which are used in designing of this ultra low power memory, but these concepts are not confined to memory, they are general in nature. They are applicable for any other circuit also. So this is the agenda for today. Introduction to low power, then active power, leakage power, and then your question answer session. First question is, why low power? What do we mean by low power? What is low power? First of all, what is power? Power is like any chip. If it works, it needs energy, right? So it consumes power. So how do we define power? Power for a chip is very straightforward formula. There is a VDD into IDD. How much, like if a chip is operating at 5 volt, how much current it takes? If it takes 1 milliampere, 1 milliampere into 5 volt, 5 milliwatt is the power. Then why low power? The reasons for low power are like, you don't want your computer to be like this, as shown in a picture. There is a table fan being used, because the chip or any circuit, they dissipates lot of power. So if that power is not controlled, you have to dissipate. If you have to dissipate the power. If you don't dissipate, it will generate heat and it will burn. If you open any laptop or any desktop, you will find where there is a CPU, where there is a microprocessor Intel chip. Normally there is a fan also, or there are heat sinks, there is a fan also. Okay, so this is one reason. And another reason, you see, if you don't use low power techniques, then the laptop will be as hot as your hot plate. Even you can make omelette on your laptop also, and we don't want to make omelets on the laptop. That is why we have to think of certain techniques of reducing power, because this Pentium chip, it takes power equivalent to a 100-watt bulb. 100-watt bulb, whatever power it generates, the same 100 watt, it also generates a 100-watt, though it may be working at 3.3 volt, but the current it takes is quite high, 40 ampere, 50 amperes. So it is a 100-watt kind of power it is consuming. Okay, so and the area is much smaller than the bulb. The surface area of the bulb is bigger, but for a chip it is smaller. So the power density is very, very high. Another reason for low power is we have lot of gadgets, like handheld mobile gadgets, which we are carrying with us. Those needs a battery to operate, right? And a battery, if it takes more power, you will know battery has a limited power capacity. If a circuit consumes more power, then it will dry down soon. So you will have to recharge it. Okay, so but we don't want recharging every 2 hours or every 3 hours. It is slightly impractical things. So we want the circuits or our gadgets to be low powered. They should consume less power, and battery technology has not advanced. The capacity of the battery is limited. And another reason is the battery, whatever the chemicals they are being used in a battery, they are same, they can explode also. Okay, so it's just like a bomb, they can explode also. You cannot put more and more power to the battery, so there is a limit to that. So what we can do is the consumption of battery, that has to be reduced. Now if you see, there are so many handheld gadgets which we are aware, iPod and things like that, which operate on a battery. More and more functionality is being added to this. When you add more and more functionality, the circuit is becoming bigger, so it will consume power naturally. More transistor, more power. So but those we have to reduce the power. Okay, so we have to try to reduce the power, then only it will be like, for a phone you want to talk continuously for 2-3 hours without recharging the batteries. So these are the scenario where we need low power. Now this is an example of a chip. It's a Pentium chip. It's a layout of a Pentium chips, this particular P3 snapshot. You can see this yellow portion, these are the memory. You see, in any digital chip, there is no digital chip without a memory. 50% or 60% of the chip area is occupied by a memory nowadays. Memory is of various forms. It is a static RAM, dynamic RAM, VROM, flash memory. Very fast. If the memory fast means the access time of the memory, of assessing the memory. So how do you assess the memory? First you send a signal, it will point, it will select the location, you will send a signal, then you will send the address bus, you will send the address, select a signal, you will send the read write signal, then you read or write. So this is assessing the memory. So where you need fast access, you make SRAMs there. SRAMs are very fast. So you cache memory is close to the microprocessor, sits on the chip, very close to chip. It's very fast. It consumes more power also, but you don't need a very large memory because it's a temporary memory. It's just like a scratch pad. Where you want to store a lot of things that can be away from the microprocessor, that can consume less power. It can take more area also because more size is required. So now this is an example. So the on-chip use of SRAM is increasing with increasing processor capacity. One, because the capacity of the processor, earlier we had 16-bit, 32-bit, people talking 48, 64-bit, more functions, more processor capability, you need a bigger scratch pad, you need a bigger memory. So the memory on this, on the chip also is increases. So now in this chip, if you can get an idea about this yellow portion, seems to be 1/3 of the total chip. So but if you see the power will, if the this total chip, if it takes P power, yellow portion is 1/3, it doesn't mean that it will take P by 3 power, it takes more power. Okay, the memory takes more power than the logic. The reason is, in a digital logic, in a CMOS, the current doesn't flow from VDD to ground. But in memory, this is not the case. There are sense amplifiers in that. There are decoders. There are sense amplifiers which consumes always power. There's always a path from the VDD to ground. So in short, memories, they consume more power. So we have to think of techniques to reduce this power. So this is the power consumption here with respect to technology. You see, you are aware of this technology node. We right now world, there are all these Intel microprocessors. They are being made in 22 nanometer. Recently, even 3-4 days back, there was a news that they have recently come. Some laptops have come in USA which are using, which are having a processor which is made in 14 nanometer FinFET technology. So they had posted some pictures, and Intel, normally all these things, sometimes they tell, sometimes they don't disclose what is the shape of the transistor, what type of transistor. Normally all these things are kept secret, they don't tell. So here now the world, when the CMOS started, it started with the 5 micron in 1980. So now we are 45 nanometer, 22 nanometer is very common. There are many fabrication plants which are making chips at 45 nanometer, 22 nanometer, even 15 nanometer also they have announced. So from one technology node to another technology node, transistor size is decreasing. But what is happening is, you see there are two types of power. One is a standby power, another is an active power. So what is the meaning? Standby power is when the chip is not working. Okay, it is powered on, it takes certain amount of power, that is known as a standby. It is not doing anything, it is powered up. When it is working, when it is functioning. Like if it's a CPU, when the clock is running, when it is adding or subtracting or multiplying, doing something, then that is known as active power. Okay, so you can see in this various technologies, this side, if you are able to see, is the current, but here it's a 180 nanometer. This blue one is the active power. This is the standby power. Okay, so active power is much more, this bar, and then the yellow portion. So when the chip is not working, it is not taking any power. Like the phone, when it is not working, it is taking less power. But when a call comes, when you are using or you are playing some video games or you are surfing the net, then it will take more power. So this is if in 180 nanometer. If you reduce the technology node, you go to 130 nanometer, you can see this blue has decreased some, but this see the increase in this yellow. You see at 90 nanometer. 90 nanometer, the standby power is around 50-60% more than the active power. And you see at 65 nanometer and down 45 nanometer, 22 nanometer. What is happening is active power is reducing, but you see this standby power. Even when the chip is not working, it is taking a lot of current. So why it is happening? When the transistor we are reducing the size, why it is suddenly taking so much current? This is because of the short channel effects. Those we will discuss in the later part or some here also. So it takes more current because of leakages. There is a tunneling effect. So all those things, the current it takes more. So now we have to basically in this we have to conserve. We have to find techniques where we can reduce both these power, active power also as well as standby power also. Okay, and the leakage power has transformed itself from a non-issue to nightmare. Leakage power, standby power is also known as a leakage. It's a leakaging because if the chip is not working, it is not functioning, it is on a standby mode, it should not take any power. So we call it a leakage. Fine. So leakage which was not there in 180 nanometer, but in the lower technology nodes, it has become a nightmare. You have to control it. Power management is there are various abstraction layer of a power management. What I mean is, you see, in any electronic device, let us take the example of a laptop or a mobile phone. All these modern smart mobile phones, it basically there is a chip. There may be few chips, 2, 3 chips inside that. Then there is a card. Then there is a software also. So these power techniques, power saving techniques, they are employed at all levels. At the top there is a software, so it is employed there also. How it is employed? The software makes sure that if the mobile phone is not being used, wherever there may be certain LEDs, like screen is there, the light of the screen is immediately switched off within 5 seconds or 10 seconds, so that power is saved. Okay, the processors, that the software takes care. There may be certain circuits which are not required, they are all switched off, they go in the sleep mode. Okay, whenever a signal comes, like if the signal someone is dialing the number, then through antenna that the receiver gets an indication that now some signal is coming. It immediately wakes up and it takes the call, and immediately the software which is governing the whole phone, they will immediately lighten up your screen also. Okay, so this way it happens. Or as soon as you press any button, immediately it knows some activity is here, immediately the circuit wakes up. Otherwise it is in the sleep mode. You can see this your laptop also, there is a screensaver, all lights are shut off. So inside the circuit, so there is a software which is doing, there are techniques of power management at the software level, at the board level, at the chip level. Chip also there are two or three modes. Three modes definitely. Those we will see. What are those three modes? So at all these three levels, you have to conserve power. You have to save power. So this even the motive of the story is like even sleep can cause hunger. So reduce sleepwalking. This means while sleeping, standby mode is sleeping. Okay, so that also it causes hunger. You need some energy for that. This is the now for conservation power, for reducing power, we should know what are the various components of the power. I am here writing in SRAM, but it is true for any digital circuit, not analog. It is true for any digital circuit. Some of these are true for analog, but not all. Okay, so total power in a CMOS. SRAM can be represented by, again, this equation is true for any digital circuit. So there are three components of the total power. If this formula may not be slightly visible, but I will read out what are the three components. I told you there are two components basically, a active power and a standby power. Standby power and active power. Standby power again has two components. One is the leakage and another is the short circuit power. Okay, so what do we mean by this? Now the dynamic power is given by alpha CV square F. This is the formula for this. And short circuit power is given by VDD into IDD short circuit, and there is a leakages power. If you want, I can explain on this concept on the board, and just for your clarity, you see what it happens is why CMOS became popular is it consumes less power. This is a CMOS gate, this is VDD, this is V in, this is V out. Now if I draw this, it will be like this. This is P plus substrate. We will have a P plus connection here. Contact, then we have N plus, we will have N plus, we will have oxide and a gate, then we will have anvil here, P plus, the gate, the P plus, N plus, and we take all these contacts. This is the transistor basic code. Okay, so now when if you take a clock here, the switching will occur. If this clock is not there, this means there is no clocking here. This transistor is off and this is on. Whatever, one will be off, another will be on. So from here to here, no current is flowing. So no power is consumed. Okay, and if you give a clock here, what happens is this then for some small time a path is developed from here to there. Okay, so some current will flow. So that is known as, that power is alpha CV square F. You can write this, that is given in the books also. So it depends, F is the frequency of this. If this is more, frequency is more, the dynamic power is more. If the circuit is fast, it eats more power. Speed of the vehicle, if you want to drive at high speed, it consumes more petrol. Okay, the same way here, if circuit is working fast, you need lot of current in that, so it needs more power, it consumes more power. If the capacitance is more, if voltage is more, if this is more, then also it takes more power. Alpha is the how much, there will be many gates in a circuit. If more number of gates are switching, it takes more power. Okay, so what other standby power is almost in a here to here it is almost zero. But when you shrink the transistor, what happens is, if you shrink means you are reducing this side. So there are leakages power. There are around 5 types of leakages in a transistor, which are happening from source to body. This is a substrate. There will be some leakages from here also. There will be some leakages from here. There will be some leakages from here. So all these leakages, they will constitute the standby power, because the channel length is decreasing. Okay, and your Tox, which is the gate oxide thickness, that is decreasing. So there are, because of tunneling effect, some current is always flowing from here to here, from here to here, from here to here, from here to here, and from here to here. And some current is flowing, so definitely it is consuming power. And as you decrease the transistor size, so this power also increases. So what are the ways to control this? So there are three types of power: active power, okay, short circuit power is, you see, when this suppose here this is zero. If this is zero, this transistor is off, this is on, right? If like at this stage, then you suddenly make it 1. If you make it 1, this will become on, this will become off. So what happens is, this was on, it will go from on to off, it will go from off to on. In between there is a time momentarily where both the transistor will be on, and there will be complete short. You've seen this inverter, CMOS inverter. So that is known as a short circuit power. For that, it is for a small time, but it is there. Okay, so that is known as a short circuit power. Now, the dynamic and short circuit power constitutes the total active power, and this dynamic power occurs due to charging discharging of capacitance. Now, the dynamic power, what is the meaning? Why it consumes power? This means, you see here, there will be some capacitances here. What those capacitances are? This is the drain. Okay, there will be C, drain to body. This is also drain, drain to body of N, drain to body of P. Okay, from here, then this, there is a capacitance here also. This is gate to drain of this, gate to drain of this. That also, all these capacitances will be added. And in a circuit, in an IC, there will be some stage here also. It will be driving some transistor. So that transistor will also have an input capacitance. That also will be added. Then this will be interconnect. It will be interconnect metal line. So this metal line to subtract, that also is a capacitance. That capacitance will also come. So all these capacitances are added. Okay, so when we change the signal here, when we change the voltage here also needs to be changed. So there is a capacitance. You have to charge the capacitance or discharge the capacitance. Charging occurs through this way, from VDD to here, discharging occurs this way, onto ground. So to charge or discharge these nodal capacitances, there may be big circuit. At each node there are capacitances. To charge or discharge those capacitances, you need active power. Fine. And short circuit, you know, from VDD to ground. Leakages, I told you, there are various PN junctions where there are those leakages power. Okay, so these power have to be reduced. Leakages power occurs primarily due to subthreshold leakages, diode leakages, gate leakages. There are basically normally three types of leakages. PN junction, you know, in a MOS, all PN junction has to be reverse biased. A reverse biased PN junction also takes reverse current power. There is a current always flowing in a reverse biased PN junction because of minority carrier flowing from P to N and N to P, right? And that is known as a diode leakage. Gate leakages, because the gate oxide is becoming thinner, so there is a tunnel. In a modern physics, there is a tunneling phenomena, Norman tunneling. So because of those tunneling, some current flows. And then there is a subthreshold region. Threshold region means, you see, we assume that a transistor, if the gate voltage is less than threshold voltage, no current flows. But actually it is not the case. Some current always flows in that, which is known as a sub-threshold current, right? So normally in the books, which like we draw ID versus VGS, this is a VT, we show that it is like this, and this curve ID is proportional to VGS minus VT square. This is okay, but it is not like this. This curve, basically, there is some current always flowing like this. So at VT it shoots up like anything. So there is some always current. That is known as a sub-threshold current, below threshold, sub-threshold. It may be in nanoamps, less than nanoamps, picoamps, but say it's a 1 nanoamp. Okay, but in a chip, if there are 1 million transistors, so you multiply 1 million into 1 nanoamp. So how much current it becomes? Okay, so when the transistor sizes are reducing, the number of transistors on a chip are also increasing. So this power also becomes more. Now, if we have to reduce the power, we have to see all these different types of power, and we have to find ways of reducing the power. So let us discuss about the active power, how we can reduce the active power, what are the techniques of reducing active power. So this is the formula for active power, alpha CV square F clock. So it can be very easy, because if I have to reduce this power, what I can do is I can reduce alpha, I can reduce C, I can reduce V, I can reduce frequency of clock. Okay, you reduce all, active power will be reduced. So this active power can be reduced. Now this can be saved. So let us discuss one by one. What is this alpha? This is the switching activity. In a circuit, there are many transistors. Okay, so when they are not switching, they are not consuming active power. When they are switching, they are consuming active power. So you have to make sure that you have to design a circuit so that the switching activity is minimum. Okay, so when you are optimizing you have learned K maps, Carnot maps. They will optimize the circuit, you reduce less number of gates, less number of. Similarly, there are software where you can see the switching activity. You have to reduce the switching activity unnecessarily. You need not do the switching. Okay, so this has to be kept in mind. Then you can reduce this power by amount of switching. Similarly, in a memory also, this in the memory, when reading and writing, more times you read and write, it will the switching in a memories, you read, you write again, you read, you write again. You have to reduce that activity if possible. You can reduce the this thing memory of into smaller subarrays can reduce both alpha and switching C. Now what this happens is, you need a memory of 1 million, say, bits. You see, 1 million bits can be organized as a one array. You understand? There can be some rows, there can be some columns. It can be organized as one array. Or you can divide 1 million in 4. So how much it will be? Say in 5 groups, so 0.2 million, 200k. 200k, you can have 5 arrays. Okay, so but in case in the original thing, in 1 million, the switching activity will be more. But in case of if you have subdivided the memory in 5 points, it will be slightly less, because these 4, if there is an action in one block, only that one block will be active. Other 4 blocks will be in sleep mode. So that way also the active power can be, we will see in further how much we can reduce. That also can be reduced. Another is by reducing the voltages, V square. If you reduce the voltages, earlier we were operating chips at 12 volt, 15 volt, okay, then 5 volt, 3.3 volt, 1.8 volt, 1 volt. This is the reason. You can see from 5 volt, if you reduce to 1 volt, so it is V square. So 25, 1 by 25 times power is reduced. Right, this is clear. So you reduce the voltage. That is happening. Even this low technology node, they are operating at less than 1 volt, 0.8 volt, 0.7 volt. But there is a limit, you cannot go down also. Then by scaling down frequency of operation, then it is capacitances. That is a technology, how you make a transistor. Your metal lines, you see, you have to reduce the parasitic capacitance of the transistor. You have to, what type of material, what type of geometry you use. You have to reduce the interconnect to substrate capacitances. So there is a limit. It depends on the technology. Then also power will be saved. Then frequency of clock. Okay, if you nowadays you have seen the laptop, it is 2 gigahertz, 2.4 gigahertz. Okay, it can operate. In the mobile phone, the same 2 gigahertz, 1.5 gigahertz microprocessors are used. Microprocessor may be 2 gigahertz, but say if you are doing certain, like maybe you are doing some addition or subtraction on a mobile phone, you need not do the operation at 2 gigahertz. Okay, very less frequency is required. For you, it is not like you will not be able to control it, but in the chip also, it knows where this high frequency is needed, then only it will operate at high frequency. If there is some activity which does not need a very high frequency, it will reduce down, it will scale down its frequency automatically. Okay, it will save power that way. In a mobile phone, when you are surfing the net, if you are downloading something, it needs very fast thing. So clock will be fast. If you are simply downloading, if you are simply surfing the net, it may not be that fast. Okay, it will automatically choose the appropriate. When a designer, the chip designer, the microprocessor designer, he has taken into account all these things. So as I told, power saving concepts, they are employed at chip level also, software level also. Software also have to do certain things. So it's a, you can reduce by power by frequency, by clock frequency. You can reduce the clock frequency, you can save power. Memory partitioning, as I told you, it is very important. you partition the memory to divide the overall capacity into smaller ones. You see, if you have studied about the memory design, there is a row bit, there is a word bit, there is a column bit. Okay, so if there is a 20 rows in that column, if the matrix is big, so that bit address, one bit will go, one line will go, which will cover the whole. It is like this. If the suppose the physical side of the memory is like this is the memory array. It may be 512 by 512. So there is one signal which is one line which is going all the way like this. So it is this much big line. So capacitance also, because this is a metal line, so the capacitance to substrate will also be here, it will be very high. Okay, so if I make some different blocks, small blocks, say 4 blocks of this. Okay, this means 500, 256. This is also 256. Okay, so here these lines are here reduced to half. The capacitance also reduced to half. Okay, so this way the one can save the memory. But what is there is some penalty in this also. Some extra logic will be added. Okay, but that also consumes power. But overall, you save on power. So these are the various techniques which are being used, because as I told in this figure, so this is 512 column, 512. This is a bit array. This is the array. There is a peripheral logic. Peripheral logic means one is a bit array, means how you store a single bit. There is a 6 transistor architecture of SRAM. So there those slots are there. Then this row address, column address, row decoder, column decoder, sense amplifier. So that is placed here. That is known as a peripheral logic, right? Okay, so this bit lines, if it is a total 512, so all whole of this line will be energized. Energized means the capacitance of that will be charged or discharged entire, and it's a big line. But if I split like this in small, then that bit line is becoming smaller. Capacitance is smaller. The energy required to charge or discharge is smaller. If you divide by 4, divide by 8, it will be further smaller. Okay, this concept is clear. So this means this is a practical example of memory partitioning data. Okay, so this side, this is active current, but you can see this on the height of this. So this one, the first one, is one, as I told, complete one, 512 by 512. So it consumes this much power. It takes current which is 0.6 here, 0.6 amperes. Then if I make a 2 bank, it becomes 0.4. This one, yellow one, it becomes 0.4. And if I make 4 bank, it is further reduced. If I make 8 bank, you can see from here to here is a massive reduction, but here to here is not there, and 4 to 8 maybe there will not be much reduction also. Why it is happening this way? Because there is some extra logic is also coming when you are splitting, when you are dividing, some extra logic that also consumes power, so that is getting offsetted. Okay, so you have to decide what is the optimum solution for this. So this, the motive, the moral of the story is divide and rule. Like you divide the memory and the rule on the memory. Okay, so this way you can design the memory. Nowadays, very huge memories in GBs, they are available. So they are doing proper partitioning of the memory to conserve power. Another is the concept of voltage island. What do you mean? You see, we earlier we told that if the voltage, the power is proportional to voltage square. If you reduce the voltage, you reduce power by square mind. Okay, so now you see, certain, if you have to read memory, certain amount of voltage is required, that you cannot reduce it. So you have to take that memory, you have to keep those voltages. Okay, but these peripherals, sometimes they can work at a lower voltage than the memory bit cells. So in a memory, what is happening is, you see, this is the memory. What happens is, this is the memory logic, memory cell. Here you have cells like this, 512 cells, where one bit is stored. Then this is the peripheral circuit. So this is an SRAM. Some data is stored in this cell. This is the peripheral, which is a row decoder, column decoder, sense amplifier. Okay, so now in this, you cannot reduce the voltages below say 0.7 volts, because if you reduce the voltages of these memory cells VDD beyond 0.7 volts, the data will be lost. Okay, but this particular circuit, peripheral circuit, if it is not in use, if it is not working, you can reduce the to 0.1, 0.2 volt also. Okay, so and when it needs to read or write, you can again increase to 1.8 volt. Okay, so these are the techniques which are used. So peripheral can work at a lower voltage than the memory bit cells. So basically means what you are doing is you are creating voltage islands. So earlier one whole chip was operating at one voltage, either 5 volt or 3 volt or 10 volt. But now there are many voltage islands in a chip. Okay, there is some section which operates 5 volt, some section at 1 volt, some 1.5 volt, some at even 0.2 volt, like that, depending on the requirement. So you save power wherever is possible to save. And then how to do the interfacing? If there is one block which is at 5 volt, there is another block which is at one block, but there are IO signals which go from one block to another block. So there are level shifters, IO level shifters. Okay, so at each stage there will be IO level shifters, and this way you can reduce power as explained in this. This is one peripheral, this is one core, so there is a level shifter here. Okay, so level shifter can be used. So this is a voltage island, is a very common concept which is used in saving power. This is one example of this. You can see here this green one, and this you can see here this green. This is a basically a memory example of a memory with the volt. This is basically a VDDP. Here I have reduced the voltages. This one is from the from, I think it is not readable. I can read out here. It is in the green one. This one, the voltages of the core and peripheral, they are both 1.32. Okay, but in this violet color one, the peripheral has been reduced to 1 volt. Okay, this means in the green one, both the peripheral and the core, the voltages are same. Okay, so like this is the memory, the voltages for this and this are same in green color. Okay, so you can see, but in this violet one, the peripheral and the peripheral voltages have been reduced. So this much saving is there. You can see it is less here, it is less here. This is active and this is leakage. Both these things are shown separately. So leakages also, when you reduce the voltages, you get some saving here also in the leakages, and you get some saving in the active also. For two only. If there are 3 or 4 voltage islands, you will get further reduce. Okay, so where how much voltage is needed, give that voltage, don't give extra. This is what the moral of the story is. Okay, like here a inverter can, if there is an inverter, it is storing some logic, it need not be given 5 volt, it can store that logic at even 0.5 volt also. All if you are giving more, that is unnecessary consuming power only. So whatever it needs, you give that only. So this is what the moral is. You see, now leakage power, we come to the leakage power. Leakage power is the real trouble. As we have seen, the leakage power is becoming more than the active power in smaller transistors in the new technology. So this, as I told you, this figure explains, this is the source, this is the drain. Okay, so as this is the gate length. So as the gate length shrinks, what happens is there is leakages as shown by this green arrow. There is a gate leakages from source to gate, drain to gate, and from gate to body. So all these currents will flow. Okay, this current through gate flows because of the gate oxide is also shrinking. So this is a because of tunneling. Though it's an oxide, but it certain electrons can tunnel through the oxide. So there is a current here. and there is leakages, and there is a PN junction also. Those currents will also be there. So then besides this, there is leakages, as I told, it's of three types: subthreshold leakage, gate leakage, diode leakage. Diode leakage is this N and this P. This is a diode. So this diode leakage, this diode leakage, and subthreshold leakage will occur from here in the channel. Gate leakage will occur from gate to body, like this. So these three components are there of this leakages. Now there are different methods for controlling these three leakages. So what are the methods? These are the equations, I think, which is not very clear here, but it is there in the PPT. You can see this. So how we can subthreshold the leakages, how we can we should know to which parameter the subthreshold leakage depends. Subthreshold leakage, it depends on the VT. It grows exponentially with lowering of VT. Okay, so what it grows exponentially with increasing temperature. If the temperature increases, the subthreshold leakages increases. It increases with the width of the transistor. There is a transistor W by L. In the formula you have seen, W is the width, L is the length of the transistor. If you use a wider transistor, subthreshold leakage is more. Okay, if you increase the temperature, subthreshold leakages increases. If you increase the if you lower the VT, you decrease the VT threshold voltage, the subthreshold leakage increases. So this we know. Now you have to tackle all these things. So like the subthreshold leakage increases with temperature. So how the temperature will increase? You have to maintain the temperature. If there is a hot spot in any chip, you have to take preemptive measures so that the heat is dissipated. How you can do? You may have to use heat sinks with large metal. You have seen heat sinks are being used on the top of the chip. If you open any desktop computer where there is a devices which are consuming a lot of power, there will be some heat sinks or some small fans. So some preventive measures are being taken to control that temperature also. So temperature cannot go beyond a limit. Okay, so these are the three things you have to take care, which are dependent on subthreshold leakage. Then there is a gate leakage. Gate leakage, what is happening is the gate leakage, it depends on the thickness of the T-ox, we call it the gate oxide. If you reduce the gate oxide thickness, the gate leakage increases. Okay, for that it can be solved by high K material, high dielectric material. There is a lot of research which is going on. For the last 25 years we have been using silicon dioxide, but now silicon dioxide, instead of silicon dioxide, you have to use high K, like Pentium or hafnium oxide are being used at the gate, okay, to reduce this gate leakages. So lot in the lower transistor, low geometry transistor, 22 and 25 nanometer, silicon dioxide is not possible because of the high leakages. So like hafnium oxide and other material which have high dielectric, they are being used. Then there is a diode leakages. Diode leakages are where there is a PN junction, okay, source drain with respect to body. So this diode leakage, as you know, it depends on the area. If you make the junction small, area small, leakages will be small. It depends on the voltages and it depends on the temperature also. It depends on the voltage. You like PN junction, if it is at 5 volt or 1 volt, if the voltage is more, the reverse current of a PN junction is low. If the voltage is more, it is more. If it is less, it is less. If the area is less, it is less. So that is why we talk of shallow junctions nowadays. If you have read in the books, there is a concept of shallow. Source drain junctions are very shallow. The reason, it has two effects. One, the leakages is more and the capacitance is also less. The leakage is also less. So nowadays the concept is of very shallow junctions. Shallow junctions means this area, this source drain, this has to be very shallow. Like here, it can be here shallow junctions only. Okay, so because, and this also can be small, like this. Okay, so here this is known as the base. It comes like this. This is known as the side wall. So there is a capacitance also. This is P. This is N. This is okay. So this becomes a PN. So this is the bottom plate. This is the side walls they call it. So this also area total periphery it reduces. So this way you can control these things. Then so these are the, now there are various other techniques to control the memory leakages. What are those? They are employed in any digital circuits also. You see, you have learned that there is a, for each transistor there is a concept of a threshold voltage. Normally the threshold voltage of all transistors are same, but if you have to control leakage, you have to make transistors which are having different thresholds. So that is known as a multi-VT. Multi-VT. Okay, you make transistors which are having high voltage. If there the transistors which are having high voltage, it will be less leaky, but it will be slower. Okay, so certain circuit which needs faster paths, you put faster transistors. In those applications, those circuits which need slower timings, you put high VT transistors. Okay, so you have a choice of transistors. So another technique is using a gate biasing. One way is you fabricate the transistor having different VTs. Another way is you have one transistor which has fixed VT, but you can change the VT by body biasing. Okay, you have you understand the meaning of body bias. This is the transistor. Transistor is having this. This is the body terminal. Okay, normally body is connected to here, but if you give some potential at this also, some voltage at this also, you can increase the VT. Okay, so you can, by, if you ground it, then it is a VT, but if you give some potential, then VT will increase depending on this. This is known as the body bias. In books, it is represented by gamma. Okay, so this, by controlling that potential here also, you can change the VT of the transistor and control the leakages, because we have seen the leakages is directly proportional to threshold voltage. So you can change the threshold voltage and you can, so this is known as a multi-threshold transistor design. Okay, so normally these three concepts, high VT, regular VT and low VT transistor. There are three types of transistor which are available. So in a particular design, you choose the appropriate transistor to lower the VT, and besides that you can use body bias also to make further transistors. Okay, so this has to be carefully chosen. There is a, you see, in a circuit there is a critical path. Okay, the critical path you should not delay, the delay should be less, so use faster transistors. But other paths you can use transistors which are slower. So you have to choose the appropriate way. Use of bigger gate length transistor is another way of reducing leakage power without increasing mask cost. Now if the gate length is, you see, in a transistor, say you are fabricating transistor with different gate lengths. Okay, the VT is not fixed. VT, threshold voltage of a transistor, varies with gate length in the same technology. If the gate length is reducing, the VT will be less or high. It will also reduce. Okay, so the threshold voltage of a transistor depends on the gate length. If the gate length is reduced, the VT also reduces. Okay, so you choose appropriate gate lengths while gate L while designing the your circuits. So these are the various concepts by which you can reduce. So this is one example of the technology where this one, this bigger, this is a memory of size 32K into 16. What does this mean? 32K into 16, 16 are the data lines. Okay, so 32K into 16, this technology is 65 nanometer. So this is the power, this side is the leakage current which is in milliampere. This is around 2.9 milliampere. This is using one type of transistor only, this line, this block, RVT, regular VT. This is using regular VT as well as high VT. You can see, and here it is coming 2.3, and this was 2.9 milliampere. This is 2.3 milliampere. So you can see from here how much you have reduced this leakage current by employing this particular transistor. Okay, so this choose horses for course, it helps. This means you have to choose the proper horses where like a Tonga horse is different than a horse which wins race. So you don't have to choose a horse which wins races for running a Tonga. This is what it means. So wherever you need a faster transistor, you put a faster transistor in the critical path. Where it doesn't need, if you are putting a faster transistor, you are unnecessary consuming more power only, finally consuming more power, right? So this is what it means. And back gate biasing, this is a very good circuit. Actually, it is not coming clear. So by using the, as I told, the gate body biasing, by using body is also is known as a back gate also, because the potential of at the body, you can control the VT, so you can control the functionality of the transistor. So by appropriating by appropriate voltages at the body, you can control the power consumption of the transistor. This is what it means. And this will only control the active power, right? So this also, I will give you an example here. This is a backgate biasing leakage data. Memory size is 512K. So this one, leakage current is close to, this is 2.5 milliampere here, this one. Okay, so this is without back bias. Okay, without back bias means without body bias. This is normally what it happens is, it's a digital circuit. You This is the body will be connected to, yes, VDD. Okay, and this terminal will be connected to ground. This is without this, the first one, the bigger one. Okay, normally if you do this one, it is like this, it is consuming this power. But if you change it, if you control this potential here by some appropriate mechanism, here you don't short it, but here you control this in the circuit, you are able to reduce the power. Okay, which is being shown here. So you can see this. This is from 2.5 and this is less than 0.3. So this much difference it brings for a 512K memory. Okay, so here we are able to control this. Normally in the book, it is normally body biases are not shown. So kick them at back and they are shut. This means only the body bias potential, that is very, very important for in controlling the circuit, and you are able to control that. Now there is a concept of power gating. What do we mean by power gating? You see, remove power where it is not required. Normally in a circuit, it consists of millions of transistors, all are powered up. Okay, some circuit, whole of the circuit is not working at one time. Only a portion of the circuit is working. The circuit which is not working, what you do, you shut down the power. Okay, and when it is required to work, you wake up, you give the power. So that is known as a power gating. So this is provide limited supply to less sufficient time to provide data retention. But what you have to do, you see in a digital circuit, there may be some latch up, there may be some flip flops. They are storing certain data. So power shutdown means you don't have to make it zero, but instead of 1.8 volt, you have to reduce the power to such a way so that it can retain that data. So that is 5 or 6 VTs, 5 or 6 threshold voltage, which is 100 millivolt or 150 millivolt. So instead of 1 volt, you give 100 millivolt or 150 millivolt. It will retain that data. Fine. So this also is used. So SRAM can be operated under following modes once power gating is introduced. So in a memory, there can be different modes. Like one is a normal operation. Normal operation is chip is working, everything is normal. Another mode is a retention mode. Retention mode is peripheral power is off. In a memory, the peripheral circuits are fully off, and the core means memory where the data are stored, memory bits are stored. Okay, so there you are getting full core supply. Another option is you can give restricted core supply. I will explain you here. That will be much easy if anything are not visible on this. You see, if suppose this is a chip. In a chip, there will be some memory blocks. These are memory cells only, memory bits. Okay, and this is peripheral. Peripheral means column decoder, row decoder, and sense amplifier, which read and write from the memory. This is the memory bits only. One bit is repeated 1 million or 1 billion times. Okay, so one is a normal mode. Normal mode is power to complete circuit is there. That is the normal mode. Okay. Another mode is you give power to this block but reduce power to this. Very good. Okay, that is another mode. Another option is this power anywhere you reduce power to this block also. Okay, so there is a sleep and deep sleep. Different companies they give different names. Deep sleep mode is the power of the complete block is reduced shut down. So instead of if the power is at say 1.2 volt, you bring it down to some 150 millivolts. And there may be certain portions in the memory. In this row we call them row and column decoders, where the power may be to 0 volt only. Okay, but if there is a certain flip flop and there is a certain latch which is storing some data, you cannot reduce the power to less than 150 millivolt. But for amplifier, you can completely shut the power to 0. Fine. So you can imagine that is a deep sleep mode. If some signal comes, then what happens is there is some circuitry here which will wake up, which will generate these signals. Okay, and it will tell the power generator here to give the power supply to all these portions wherever needed, and immediately the circuit wakes up within no time. Okay, the power is cut and the power is given. So that those circuits you have to introduce. Okay, it is by explaining it seems to be simple, but implementing is not that easy. So a lot of things you have to manage. Data should not be lost. Okay, when you are changing all these things. Okay, so there is a power gating. That is the concept of a power gating. So there are circuits which shut the power and give the power. So those circuits have to be designed and put wherever it's needed. So the circuitry, the design becomes complex, but you save on this power. So this is a use of a header. Now you see the power. This basically means power can be shut from the VDD side, or it can be shut from the ground side. This is what it means. So when you can have a circuit here at the where you are giving VDD, here you will have a circuit here, and here you have a circuit. Okay, this is power circuit. Power, this is footer or this is header they call it. Okay, so there will be appropriate circuit you have to design. So they can cut, because if you cut from the here, that if power supply, you can cut from it. If you can give 1.8, but you cut the circuit here, no current will flow. Okay, or you keep it here, you cut from here. It is one and the same thing. Or you cut from both. Cut from here also. Cut. So different architectures are possible. Different companies are using different ways. But the circuit becomes very complicated, as you have seen. By using these kind of thing, it becomes very complicated. But you can reduce on the power. So this is a trade-off. So there are so many techniques are there, but it is a complicated trade-off between this. So peripheral power can be switched off while core is still powered by full VDD or retention VDD. So there are various power gating. Now you see here the transistor which are being used for power gating, those have to be designed very carefully, because those transistors need to be very fast. Okay, because they are responsible for giving the signals to the peripheral or the core, when to become up, when to become down. So those things have to be, it cannot be delayed, it has to be very fast. So those transistors, they will consume more power also, because they need to be fast. Okay, so but overall you will save on that power. So this power gating circuit concepts, they are very commonly used in a complicated memories. You can use these concepts. So this is basically what it explains here. Okay, so now power gating sizing consideration. So use high VT gating transistor to reduce leakage, size the big gating transistor to minimize the performance degradation, distribute into smaller transistor across the peripheral. So these are the various techniques by which we have told we can reduce the power. Another is we talked about voltage island. There is a concept of frequency island also. Frequency island means each circuit does need not operate on a single clock. Okay, like a microprocessor which you say 2.4 gigahertz, the entire chip does not operate on 2.4 gigahertz. Only the critical paths, they operate on 2.4 gigahertz. Some paths may be operating at few kilohertz only. Fine. So wherever needed, certain portions of the memory, though from the outside you are giving 3.3 volt, but inside there may be three requirement of 1.8 volt, 1 volt, 200 millivolt, many voltages. But those voltages you cannot give from outside. You have to generate from inside only. Inside the chip you have to generate. That is known as LDO, low dropout voltage regulators. Okay, buck converter, boost converter. So LDOs, this is the concept, because within the chip from the outside it will get only one power line. But if the chip needs 5 or 6 power levels, 1.8 volt, 1 volt, 1.2 volt, 200 millivolt, you cannot give 5 lines from outside. Outside you will give only one battery, 1 cell, 2 cell, 3.3 volt. Okay, so within the chip you have to generate this power management also. Okay, then active circuitry, when to wake up, when to put in sleep mode, those also you also have to generate. So this is the complexity of generating these signals. Understood? So in the we will cover there is one test case which Professor Mehra has scheduled for tomorrow. So we will consider the case of LDO, which we have designed a low dropout regulator. We will bring out what is an LDO and how it is done. So that is for tomorrow. So this for this time being. So you are clearly now this we will first take example for a power gating. You see, this is a standard mode. This one, leakage current is 2.5 milliampere. This bigger block. This is a standard. This is 32K into 16, 65 nanometer. Process Intel process 65 nanometer. 32K into 16 is the memory. So it is one standard mode. Entire chip is power off. This block, peripheral power is off. This one, peripheral power off, core full supply. This one, peripheral is completely off, but memory core is giving full. Green block, peripheral power off, but core to retention voltage. This core has been retention voltage is around 600 or 650 millivolt for a memory. You cannot reduce the memory voltage to less than 600 or 650 millivolt. Why? The reason is, in a memory there are two cross coupled inverters. So in an inverter design you can see that you cannot reduce, if you reduce the power supply of an inverter below 600 or 650 millivolt, it does not work properly as an inverter. Okay, so that is the retention voltage. It retains state till 600 millivolt. Beyond that it doesn't. Peripheral, they are not retaining any state. You can bring it down to 0 volt. True, but retention you cannot, because then it doesn't work as an inverter. So this way you can see how much saving it can occur. So this means the moral of the story is stress resources only when it is needed, and as and when on as much needed. So this is what the whole topic of low power design, and if you have any questions you are most welcome to ask. The concept, you see, this VLSI, it started in 1980 or 80. CMOS came into production in 80-81. So that time it was a 5 volt, 10 volt, very simple 1 megahertz, kilohertz kind of thing. Very less functionality also. The first computer was very simple 8-bit computer, less big one. Nowadays you can see a lot of in one device you have TV, you have RF, you have memory, you have processor. Now you are trying to put sensors also. There are various sensors are being built in CMOS. Like in a mobile phone is an excellent example. Okay, you have put an accelerometer which can sense, like you rotate it, immediately the text will come appropriately. So there are a variety of sensors. They are also built on silicon. So those accelerometer is there, bolometer is there. So those are being there, they sense what is the direction and appropriately adjust that. So these kind of things have come up, and you are able to integrate this on a single platform, on a single substrate. which is silicon, because it is very easy, the cost is less of processing is silicon. But new concepts, the design is becoming more and more and more complicated. Okay, because if you add to more functionality, so these techniques, otherwise you make a simple memory, you power with 1.8 volt, no issue. It will be a simple circuit, but it will take more power. And once you employ these power techniques, the circuit is becoming complicated. Okay, but it is saving, as we have seen, some lot of power it is saving. So that is why, if you see the old, when this mobile phone came around 15 years back or 14 years back, it used to be always on that time. If you have some older, some 15-year, 20-year-old mobile phone, you can think the screen doesn't go up. See, same was the case with computer desktop. Okay, only when more functionality, high speed, more functionality, more functions were added. Now you see immediately it doesn't. The screen is shut down immediately. Okay, so there are various concepts which are being added in this low power. Then only the circuit works at a low. And now this is open for any question. If you have any question, please ask. All connected centers, if you have any questions, you please ask.
Hello, sir. Hello.
Are you able to hear my voice?
Yes, sir. Sir, Buddha Prakash Sharma. Hello.
Yeah, I'm okay. Please carry on.
हाँ सर, one question is there. सर जो जब when we talk about multi threshold CMOS, so उसमें multi threshold का meaning क्या होता है सर?
Multi
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 threshold CMOS में
multi threshold का meaning, multi threshold CMOS meaning, you have transistor which have different threshold voltages. Okay, so you have 3 or 4 types of transistor. The threshold voltages are different. For example, one transistor threshold voltage is 400 millivolt, another 600 millivolt, another 700 millivolt. So now you will ask why you need 3 or 4 different types of transistor. The reason is, the higher the threshold voltage, the lesser the currents, lesser the power it consumes. Lower the threshold voltage, the more the power it consumes, and the faster the transistor will be. Okay, delays will be less, the transistor will be faster. If the threshold voltage is higher, less the power it consumes, but it will be slower. So you have flexibility of choosing these transistors in a path where you need more speed, where you need less delay, more speed. You can choose the transistor with lower VT, but it will consume more power. That is on anyhow. If you want more speed, you have to give more power. But there may be certain cases where that speed is not required. So you choose a slower transistor. So you optimize on the power.
Okay,
Is
sir.
it
Sir,
clear?
can we control the leakage current with the help of threshold voltage?
Yes. Leakage current is directly proportional to threshold voltage. You can control it. Leakage currents, as I told you, there are 3 types of leakages. One is a gate leakage, that is not dependent on threshold voltage. There is a sub-threshold leakage which is dependent on leakage on this threshold voltage. Then there is a PN junction leakage which also is not dependent on threshold voltage. Okay, that will not reduce, that was dependent on something else. There are 3 factors, as I told you in this. There is a voltage, there is an area, there is a diffusion concentration. Those current depends on those. Then temperature, of course. Okay, so this have to be kept in mind. What are the different components of leakage current, of leakage power? Those should be studied thoroughly. And then which leakage power, which depends on what. So here sub-threshold leakage we can control by this threshold voltages. Other we cannot control. For other, there are different ways of controlling. Is it clear or not?
Is there? Sir, if we talk about 256 cross 1 memory and another one is 64 cross 4 memory. So what is the difference between this memory in terms of power?
The 256 one will consume more power. The reason it is having more memory cells. Each memory cells will eat some power. So more memory cells, more number of more power is required. The bit line, the word line will also be more because the memory is more. So if you see the architecture of the memory, there is a concept of word line and a bit line. There is one line which goes to the entire memory chip. Okay, so if the length of that line is more, the capacitance is more. So that capacitance, you have to charge that capacitance and discharge that capacitance. So charging and discharging it takes more current. Is it
Hello.
clear or you want more explanation?
वो उधर से कर रहे हैं। Hello,
Yes, yes, please ask.
sir.
Please re-explain.
Please explain again, sir.
About the
Hello.
about memory.
हाँ, about memory, sir. 256 cross 1
Huh?
memory.
Hmm.
How it is differ from 64 cross 4 memory in terms of power?
256 cross 1 and 64 cross 1.
64 cross 4. नहीं वो बता देंगे।
उसको बोलो दोनों 256 जो है मेमोरी आर्किटेक्चर में कैसे पावर कम लगेगा उसमें ये बताइए।
Are you able to see this board? Are you able to see the board?
Yes, sir.
लाइन होती है अरे यार
128. 256. Which one? 256.
दोनों 256 है दोनों में
वो कर रहे हैं।
ठीक है
That's fine.
Yes, sir.
दोनों में क्या
Now, if I want to make a memory of 256 bits, I can organize this way, and this also.
बोलो कि आवाज
I can organize in these three things: 256 cross 1, then 64 cross 4, 128 cross 2, right?
Yes, sir.
Now, what happens is this one will take more power because there is a one bit line which goes from here to here. One bit line will be there. Okay, and this bit line connects to all these cells like this.
Okay, sir.
This is a bit line and it connects to this. So length of this is more. We have to reduce the length here. Or this may not be practical enough. You cannot be, or access time will be low because you are getting it from here and it has to reach at this end. The capacitance will be more here. You will need more power to charge that entire line. Okay, and that will restrict the access time also. Okay, so this architecture of the memory is very important. Which how many should be X and Y? This is important. It depends on this. And here this one earlier one 256 cross 1 will take around 3 to 4 times more this thing more power than if you have X and Y same. For
Okay,
this,
sir.
and for this, if you want further thing, you see, you have to understand the concept how the memory is organized, how the bit is organized, what is the concept of word line, what is the concept of bit line. Maybe when we organize this course next time, I can suggest we can have 1 or 2 lectures on memory design. So then you can appreciate more. But for the timing, you can assume that it has to be a square. If aspect ratio is more high, it takes more power as a thumb rule. You can, for the time being, you can take it. What is the meaning of word line, bit line? This either you can refer to some book or maybe you have to wait for the next ICT. Or please, any other question?
Thank you, sir.
Hello.
Yeah.
Sir, this is Neha from SRMS CET. Sir, I just want to ask you what is the process of deciding the range for high threshold and low threshold for empty CMOS?
Yeah, this is the designer. If you are designing a circuit, you see when you design a chip, like they give you some constraints, like this should be the speed of operation. This is the power consumption. Okay, so this is the access time. This is what. So they will give you a list of specification. So you have to design a circuit and meet those specifications. So if the power dissipation has been given to you as 500 millivolt or 100 millivolt, so like I will give you an example. This last year we were designing some ADC. It was a 14-bit ADC. It was supposed to work at 20 megahertz analog to digital converter, and they wanted the power it should consume to be 120 milliwatt. But when we completed the design, we were getting close to some 850 milliwatt power, which was 6 times that power. So then the entire concept, the entire architecture of that ADC had to be changed, because in ADC there are a lot of op amps, there are a lot of OTAs. So we studied each OTA, each op amp, and then tried to reduce the power, and we were able to reduce that power to close to 100 milliwatt. So this is how the user who gives you the specification. There is a target, like you have to reduce, you have to contain the power to within this limit. If there is no such thing, then it can take any power. So then based on you have to decide, because your objective, your aim is to reduce the power as little as possible, as less as possible. As some of the slides you have seen, like this memory partitioning, if we are doing, no? So it is reducing the power, but it is adding some extra logic also, which takes more power. Overall power reduces. But then the stage comes, you are unable to reduce it further. Then it starts increasing. What I mean is, like these things. What I mean is, if this is the power. This is it takes this power. So you start employing these techniques to reduce the power. The power will start coming down. Okay, but in these techniques, there is extra logic that also consumes power. Okay, so total power is it is coming down, but it will come down. It will come here. But if you still keep on adding these techniques, then it will start rising again. Okay, so you have to settle somewhere here in this region only. Otherwise, then again it will start increasing. So it is not that you will keep always down and down only. You will keep on reducing. So there is a level below that you will not be able to reduce, because you see this multiple VT. If there is a single VT transistor, it is easy to manufacture. All transistors are same. The process steps are less. If there is two VTs, so implants will be, there will be number of steps will increase. The implant will be different. Implant steps will increase. The cost of production will increase. Okay, so the each design decision, there is a consequence of that also. So the cost of fabrication also increases in case of multi VT. So this, but overall, if you see, maybe in terms of power reduction, it is basically it is the economics which decides the. Any other question?
Good afternoon, sir, from SMIT.
Yeah, good afternoon.
Hello, sir.
Yeah, please ask.
Sir, if output signal will decrease, then the gate leakage will increase. Yes, sir. Sir, am I audible?
Now you are, yeah, please repeat it.
Give me several answers.
Plan question.
So memory
Sir, if oxide thickness will decrease, then gate leakage will increase. So, sir, you told to use some other materials instead of silicon.
Yeah, you're right.
Sir, can we know on what basis we can use the other materials and uh, uh, what are the characteristics? On what basis we will use some other materials? Can you tell, sir?
Yeah, definitely. It's a very good question. Good, you asked this. Now I will explain. Now, is this board is clear, visible to you? What is the concept of scaling? Concept of scaling is this is length L, this is P of. Okay, this is length of the device, length of the channel. Now, when you reduce and there is some voltage V, so the concept of the scaling is you reduce all dimensions by any factor. Okay, say you are reducing all dimensions by 30%. So you reduce all dimensions means all vertical and horizontal dimensions. This is the horizontal dimension. This is the vertical dimension. This is the vertical dimension. You reduce this by 30%. You reduce this by 30%. You reduce voltages also by 30%. Reduce heating by 30%. Threshold voltage by 30%. And you increase the concentration. Here it was N plus concentration. You increase this concentration by 30%. All other things have to be. This is known as a constant field scaling. Because electric field is what is the definition of electric field? It is voltage by distance. Okay, so if voltage is also I am decreasing, distance also I am decreasing, the electric field remains same. Electric field is not increasing. Okay, so in that case, this is one constant electric field scaling. There are three types of scaling. This is one type of scaling. Now the question you ask, so we have to reduce this here. Now why we have to reduce? Because there is a this here is given by along permittivity, right? This is the question here. And in the current equation, what is ID? ID is UN here W by L dps minus dt to 1 plus lambda. Okay, so this matrix is coming there. You have to increase P-ox, then only you will get more current. ID is proportional to P-ox. To increase P-ox, permittivity is fixed. It's a physical parameter. And you cannot change of silicon dioxide. If you are using silicon dioxide, you have to reduce P-ox only, P-ox will increase. But if you reduce this thickness, there is a concept of tunneling. The current tunnels through this. So there is no leakage. What I can do is I can use some other material, a hafnium oxide. Okay, if I use a hafnium oxide, I can have it more here. But since the epsilon of hafnium oxide is say 14, whereas silicon dioxide it is 3.7. Okay, so here instead of 3.7, I am this epsilon of hafnium is 14. So this means that this P-ox can be 4 times. This thickness 4 times as compared to silicon dioxide. Now, I think the same here. You understood this or not? This is the concept. So below 45 nanometers, silicon dioxide cannot be used. Okay, so we are, a lot of research is going on. There are around 5-6 materials. Hafnium oxide currently is being used. There are some other material, tantalum oxide, and there are other material also. So this is the because the COX Cox has to be increased. That is the purpose. Now you will ask why Cox capacitance has to be increased. You see how the current flows from here. What is the basic? The current flows, you have to create a channel here. So basically there is a capacitor phenomena. Capacitor phenomena is inversion will occur. You give a voltage here, inversion will occur. If the coupling here is more, the channel will be more stronger. Coupling is now in terms of Cox. If the Cox is more coupling, more electron will come here, channel will be more strong. More current will flow, and this the formula also shows that. So Cox, we have to increase Cox. Then we can go only by reducing Cox. But when we reduce Cox, the current flows here also. We don't want. We want current to flow in this direction. Okay. Is it right? Any other question, please? So we can take a break for 15-20 minutes and for tea, and then we can reassemble again. Okay, thank you very much.
So participants, please have a break of 15 minutes, and then we'll back around 11:30, and we will continue with our session with our HS Jatana ji. So still, if you have any